All right. So I think my screen is,
Yeah, it is visible.
it is visible. So we were somewhere over here. Um, just a minute. I, okay, I'll update it later. Okay, um, can you complete this design? So it is useful to see here we have considered two FSMs, ME and MD. So there's a optimization of ME was shown. So why don't you take up MD? Okay. So MD is shown over here. This is MD. So why don't you take up MD, follow the same procedure which was outlined yesterday, and then you can also post it for us to see. Okay. So take up this machine and optimize it yourself as we had done yesterday. So why didn't you apply the optimization procedure on MD? And you can just show the results also. You can post a screenshot, some of you, so you can see how you're progressing. So this kind of margin table you have to construct. So both of them have the same number of states. That means ME, we just take it up earlier, had 6 states. This one also has 6 states. So you'll have a margin table of this size. Of course, the entries will be different. So first of all, you create the margin table and post it. Let us see what you are doing. Okay. Create the margin table and post it in the chat.
Excuse me, sir.
Yes.
So what do we do like for A, the output for I1 is
Let us take up AB. Okay. Let us take up AB. So we are looking at MD, right? So let us take up AB. So if you want A and B to be compatible, okay, then the uh, uh, there is no dependency at the moment. Okay, because uh, as you can see here, the next states are not defined. So A and B can be compatible. Okay. So now you consider A and C. So if you consider A and C, well, here C and F must also be compatible for A and C to be compatible, right? C and F have non-conflicting outputs. But so if you apply I2, so A will go to C and C will go to F. So you should get the same output for applicable sequences for C and F. All right. So like that you construct the table. Okay. So carry on, and once you're done, you can take a snapshot and post that. So you can populate the Marget table and post that. How far have you progressed? Have you finished? Someone can post it. Hello, someone should post it now.
Sir, I've posted it in the chat.
Yeah, posted. Okay. Let's see. Hmm. Is it possible to rotate it or open it in? Is it possible to, is it
I'll
possible
repost it.
yeah, no, is it possible to save that thing in, or is it possible to open it in a separate application from the chat? What is this?
You have to save it and then do it.
Just a minute, let me see. Download. What has been, I don't know. What is this download? Or is it downloading? I don't know what it is downloading. Can you, Pavitra, how to save it?
Wait, let me try to save it. Let me try to save it.
Copy image. Okay, so image has been copied.
Copy image, then maybe you can paste in some other application.
I hope so.
Or let me rotate and post.
No, I can. No, if I can save it, I'll be able to post it also.
Sir, I posted the rotated version.
No, it's okay. That's all right. I'm just saying whether, I don't know. What is this? Okay, so let us look at this. Yeah, it's a bit complicated. All right. So let us check. AB seems to be okay. AC will depend on CF as we had noted earlier. Then what about AD? AD will depend on BE or EB. All right. And AE apparently has a conflict, yes. And AF also has a conflict, right? So BC depends on EF, okay? And BD is okay. BE is also okay. And BF depends on EC. So BF depends on EC. Okay. Then CD apparently CD. Okay, CD is okay. CE. What is it? CE. Yeah, so CE has a conflict. Then CF will depend on FC. All right. FC. Why have you put it in this box? Why have you boxed
Sir,
it?
it's a trivial dependency.
Oh, yeah, CF and F. Yeah, so it depends on. All right. And D apparently is not DE has DE has a conflict. DF also has a conflict, and EF, okay, A, B, and C, D. All right. So this seems to be okay. So now, can you construct that graph, compatibility graph? So the next thing, okay, so I think everyone in the class can, take this as a reference. So if you have, okay, so he has crossed out EC here. So let us see. So it depends on EC. So EC doesn't work out. EC, these are not compatible. So anything depending on EC will also not be compatible. So this has been crossed out. All right. So that's the reduction on the table. All right. Um, so this one is essentially a take because it's a trivial dependency. Okay, so now starting with this, can you construct the compatibility graph that we had seen last time? So so this is what the so you can construct the compatibility graph. So why don't you construct the compatibility graph? Actually, the compatibility graph is shown here. So let us go with that. So you can see that basically say EF. So EF depends on AB and CD. So EF, you can see it depends on AB and CD. All right, and similarly BC depends on EF. All right, and some of these, for example, BD is fine. AC is also okay. AF, what is that? No, AF, CF is sure. Yeah, sorry. AC, what is AC? Yeah, AC depends on CF, right? CF is shown here. So I think this is CD. CD is also, yeah, doesn't have any. So this is your compatibility graph. Now, starting with this compatibility graph, you can determine, so you can identify a closed set of compatibles. Okay. So can you identify a closed set of compatibles with this? Yeah. Well, it is shown over here. So AB, CD, and EF, these three form a closed set of compatibles. So after that, can you construct this reduced FSM for MD? Can you construct this reduced FSM for MD? So you got to refer to the original table, and so you're calling it alpha, right? So So as you can see, if you are grouping AB, so on transition I1, B has a transition to E. So this alpha will have a transition to the set containing E. So that is gamma. The output is 0. So like that you can construct this table. So you can go ahead and construct this table. That is how you get the reduced FSM for MD. So I think we should do one more exercise. So why don't you take up MF? Why don't you take up MF and redo the exercise? Why don't you redo the exercise for MF? All right. So for this we have seen the results. You can do it for MF as well. So please carry out that exercise for MF, and you can similarly post your margin table in the chat box. Yeah, so someone can post it. Someone can post it in the chat after constructing the margin table. Yeah. So who is going to post this time? Someone can post this time. Someone else. Ishan, are you there? Ishan? Hello?
Yes, sir, I'm present.
So, can you post it?
I'm still solving, sir.
So, who has finished? Swati, have you finished? Swati, are you there?
Yes, sir.
Have you finished? Have you done it?
No, sir, I'm still doing.
Are you stuck or are you progressing?
Progressing, sir.
So, anyone has finished?
Yes, sir.
Who has finished? Okay, so if you have finished, you can post it. We can see what you've got. Yeah, you can post it. Yeah, Anubhav, I think. Okay, all right. So let us look at this. Okay, so this is. So let us compare it again with. This one was. This is which one? This is MF, is it?
Yes, sir.
This is MF. Okay, so let us check. So A and B, well, yeah, it will depend on compatibility of C and D. And A and C will depend on the compatibility of CD and DE, all right. AD will depend on CD, okay. And AE will depend on AC, okay. AB depends on, sorry, AC. AC depends on CD, no, what is it? Sorry, this is BC. BC depends on AB, right. BD depends on AE and DD. BD depends on AE and DD, yes. And BE depends on AD, okay. And CD depends on BE and CC, okay. And CE. Look at DE is not compatible, these are not compatible, so this one Gauss, and this one also Gauss, and AE. Okay, so there is a cascading effect. So some of these also become incompatible. Okay, so good. So now that you have got the merger table, please go on to construct the compatibility graph. So someone can construct the compatibility graph and post that here. So can you construct a compatibility graph and post it here? So this is okay. We've studied this.
Sir, why does AB depend on CD?
Why AB depends on CD? Let us see. AB. So let us look at the table for A and B. So here you can see that on input I4, A makes a transition to C, and B makes a transition to D. So now suppose the machine is you start the machine in states C and D. So for subsequent inputs, you should still have the same outputs for applicable sequences. So in this case, well, as you can see, for C and D, so I think that answers your question. Now, for C and D, as you can see, the the it's I mean C and D will depend on C and D will depend on B and compatibility of B and E, because on inputting I1, C goes to B and D goes to E. So B and E must be compatible. So if you look at C and D, so it depends on BE and CC. So CC is a trivial requirement, but BE is non-trivial. So it does depend on BE. All right. So you can construct the compatibility graph now. So have you constructed the compatibility graph, anyone? Can someone post the compatibility graph for MF? Oh wait, okay, fine. Aritra, sorry. So Aritra has posted the compatibility graph of MF. All right, good. So now that you have posted it, so what about, so you next need to identify a closed set of compatibles, okay? So what will be your closed set of compatibles?
So we can take CD, BE, and AD.
CD, BE, and AD. So that covers, yeah, but now, so yes, so CD, yeah, so that's interesting observation. So you want to take CD, BE, and AD, okay. So now, when you take CD and AD, you find that D happens to be in both the sets. All right. D happens to be in both the sets, right? But you cannot combine them into a single one as ACD, because AC, as you can see in the previous thing, sorry, AC, as you have seen, is an incompatible pair, okay? AC is an incompatible pair. So if you wish to go for this one is a little tricky. We'll look at that. Do you see any other possibility? I mean, over here, if you, so you understand the problem with this. If you try to, construct this, then D is in both the sets. So you have to treat D a bit carefully, all right? Got to treat D a bit carefully. So well, I mean, the only standalone pair is CE. I mean, if you take CD, this is a cycle, so you have to take all of them. So one option is you take CE and you keep the other state singleton. So you just reduce one state. So in that case, you'll have 4 states. So that's one reduction where you have 4 states. You combine just C and E. Okay. All right. So we will revisit this thing. We'll revisit this. So at least you understand that this is an interesting situation. All right. So we will come back to this. So before we take that up, so I would ask you to, let us say, work on this machine. Just try to work on. So this is a smaller machine. Okay. Why don't you carry out a similar exercise on this machine and see what you get? So maybe I can also do it. Close that. So I'll just put it here. Okay. So here you have got, and if we again go the same way, as we did earlier. Just a minute. So here, let us take up. So this is your table. Okay, maybe you can. Good. All right. Oh, so what about A and B? So AB depends on AB and it also depends on BC, right? AB depends on BC. What about AC? AC is clearly incompatible. And what about BC? Well, BC depends on AB. All right. So let us have AB and then you have BC. You have a similar situation, right? AB depends on BC and BC depends on AB. But you can't, as you can see, you don't have, this one is not present. So you have this state, you have the state here as well as here. So we come to the concept of state splitting. So that is what we have done here. So if you look at this table, we have split B into two states, B1 and B2. We have split B into two states, B1 and B2. All right. Now note that what we are doing, so we are not increasing the number, at the end of the day, we are not increasing the number of states because one copy can, be made compatible with A and another copy can be made compatible with C. All right. So this is what we have done. This is what we have done. So we have got, let me just copy it here. And well, on I1, and this is on I2. All right. So what we have done is A0, C0. Now this we are sending to B1, the output is 0. And this we are sending to B2 with an output of 0. Just a minute. All right, so Here it is B with an out. Let me just put a gap there. B with an output of 0. B with an output of 0. Maybe I can. See, I can move down a little bit. Here I've got B1 with an output of 1, and I've got A with an output of 1. All right. So this is what I've got. Now I can instantiate B in two ways. Okay, let's just see. Okay. I've got let's put it here then. More easy to distinguish. Okay. So I've got all right. So I hope you understand this. So we have split B into B1 and B2. Okay. So as you saw that we are, B needs to be compatible with both A and C. So when you are trying to combine AB, you need a B which is compatible with C. All right. You need a B which is compatible with C. So this B2 we want to make compatible with C, and similarly you also you're making a transition to B. So you need a B. So when you make a transition from B to B, you need a B which is compatible with A. All right. So when you make a transition from, you also need a B which is compatible with A. So this is what we have. So B2 has been, the outputs have been chosen so that B2 and C can be compatible, and here the outputs have been chosen so that B1 and A can be compatible, right? So this is called state splitting. Now note that over here I put it as B. So here you have two options really. You can make B compatible with. You can put it here as B1, and here you can put this as B2. So these are two options that you have. Okay, the two options that you have for this B. So accordingly, you get two machines. All right, you get two machines. So you understand the idea of state splitting. So in a situation like this, where B needs to be compatible, if you want to reduce it, then this incarnation of B needs to be compatible with A, whereas this incarnation of B needs to be compatible with C. So that's what we did over here. And when we do that, well, we get an option here as well. I mean, that is for this particular machine. So, so as you can see, what we really have is we can have, so we are making A and B1 compatible. So A is compatible with B1 and C is made compatible with B2 here, all right, after state splitting. So B is split into B1 and B2. All right. So
Excuse me, sir.
yes.
Sir, could you please explain it on the input 0? Why from state V1 we are going to B1 comma 0? We may also go to B2 comma 0.
Yeah. So both options are taken into account, right?
No, sir, from state V1.
From state B1. Okay. So from state B1, so if you look at the original machine, it is going from B to, B with an output of 0. All right. So, so we keep the transition to the same state. Suppose, okay, let us suppose that if you make a transition to B2, let us see what happens. Okay, so if you make a transition to B2, then you will need A to be compatible with B2, right? You will need A to be compatible with B2. So then that's not going to happen. The way we have designed this machine, A will not be compatible with B2. As you can see, there is a conflict with this incarnation of B. So if you keep it as B1, then A can be compatible with B1. If you make it B2, then A cannot be compatible with B1, right? Because in this case, if you want A to be compatible with B1, if you keep it B2 here, then A must also be compatible with B2. And if you see here, A, there's a problem. So A and B2 will not be compatible. All right. So it is better to keep it at B1 rather than B2. All right. If you want to reduce the states, I mean that is the objective of state splitting anyway. All right. So now we can go back. We can go back to this situation where, so here also there is a need for state splitting. So if you can split D into D1 and D2 so that say D1 is compatible with C and D2 is compatible with A, then you can have this reduction, right? So why don't you try to do a state splitting for this machine and see what you get. All right. So please try out state splitting here. Try to split D into D1 and D2 so that D1 is compatible with C and D2 is compatible with A. So you can work out and you can post your result over here. Yes, so have you tried out state splitting for this machine? Yeah, can you do it? Why don't you try to proceed with the merging of CD, BE, and AD with state splitting, splitting D between C and A. Well, has anyone made any progress there? Ronak, are you there?
Yes, sir.
So have you done it?
Sir, I'm trying.
Okay. What about Shayoni? Shayoni, are you there?
Yes, sir. I'm trying, sir.
Trying. So you can post your intermediate result also if you have not completed. Whatever you have done, you can post. Any intermediate thing also you can post.
Sir, in the after the splitting, can the states that are created still have undefined outputs?
Yeah, I mean, you can define the outputs later on, but immediately after the splitting, you don't have to define the outputs. Finally, when you realize the machine, you will have to define the outputs, but immediately after the splitting, you did not define the outputs.
Okay, sir.
Hmm.
Sir, I've posted it in the chat.
Okay, good. Let us. You have posted the final thing. You post the intermediate one also.
Okay, sir.
Yeah, because without that it is difficult to follow. Pavitra, can you post your the intermediate one? The intermediate.
Yes, sir. I'm doing that. Yes, sir.
Anyone, I mean, anyone else can also post if you are done. Yeah, others also please do. Okay, so let us see. So we want to merge. What do we want to merge? We want to merge. Let me just write down here. We want to merge. Sorry. See, we want to merge. We want to merge AD, CD, and BE. All right. So this is what we want to merge, and this is the intermediate margin table that he has posted. So we can interact. So let us see. So we want to merge. So here, of course, there is a question of splitting. So let us write it this way: A, B, C. Yeah, here's also written at D1, D2, and E. All right. So let us consider merging of B and E first, because those are easier, right? Because they're, I mean, let us just see what is happening. Let us try to merge that and see what happens. So B and E, okay. So maybe we can try to put them in a separate color. B and E, let us put in a separate color. So B makes a transition to E. Yeah, so we have to put the inputs. Okay. We have to put the inputs. So inputs are I1, I2, I3, I4. So first let us look at merging B and E. So B makes a transition to A1. So A with an output of 1. What about E? So E also will make B and E, right? We are merging B and E. So here, this is as such, don't care, but since we are merging them, so I'm just, this was originally don't care, so I would like to make this also A1, right? So that it's a trivial. Now here it is there also, since both are don't care, I leave them as they are. Here also both are don't care, so I leave them as they are. Here it is going to D, okay, it is going to D and with an output of 1. And E is going to A with an output of 1. So, yeah. Now, if you look at this earlier diagram, so let's also have this earlier diagram. We can just so here you can see CD depends on BE, okay? CD depends on BE, BE depends on AD, BE and AD, let's just make it bigger. CD depends on BE, BE depends on AD, and AD depends on CD. Okay. So these are, so now, so BE depends on AD, okay. So let us just see what he has done. So Amit, have you merged A with D1 or A with D2?
So A with D1.
All right, so he has merged A with D1, okay. So we would prefer to keep it D1, okay, so that, you know, you don't want to get extra conflict. So let us say we want to merge A with D1. So it is better to keep, this dependence with D1, okay. All right. So we have done that. Now next, so A and D1 he wants to merge. So let us just put, so this is, important to note that this is D1. We are putting it as D1. Okay. Maybe you can put it in. All right. Now, maybe we can E and D1 we can put in, say, green A and D1 and then put in green. All right. So, yeah. So let us see the entries for A and D1. So now D1 has a transition to E with an output of 1. So here also this is as such, but because I'm merging A and D1, I would like to make a transition to E with an output of 1, right? So now this is going to C with an output of 0, and this is going to D with an output of 0. So this is, so I need C and D. So I want to merge, I want to have C. So this should be D2 because D2 I would like to merge with C, right? So that's why I would like to keep that as D2, all right? So maybe I'll just indicate that with, I'm choosing this as D2. And let us see I3. I3, A on I3 is going to, D1 on I3. Okay, A is going to D on I3, right? And with an output of 0. And this is don't care. So here I have an option, right? I have an option because this is don't care. I can choose it as either D1. I can choose it as D1 and keep this as D1 and put an output of 0. Or I think I can also keep it as D2. All right, I can also keep it as D2 with an output of 0 because because both of these will give rise to both of these options will give rise to trivial dependencies. So either I need D1 to be compatible with D1 or I need D2 to be compatible with D2. So both will give rise to trivial dependencies. But of course, I shouldn't make one of these as D1 and the other as D2. All right. So I think here I have an option. All right. Let us go to I4. So I4, the output is C. Output is C. This is don't care. And D, the output is D. So here, of course, I should not put it as, say it is D, and the output is 0. So here I should put it as D1, because if I put it as D2, No, sorry, it should be D2 rather than D1. So, because here C and D must be compatible, so we want to merge C with D2. So, this one should be D2, right? This one should be D2. And here I can choose the output as, 0. Output is 0, so that, these two remain compatible. All right. So now let us go to C and D2. So C is going to B with an output of 1, and D2 is going to E with an output of 1. On input 2, it is going to C with an output of 0. D2 is also going to C with an output of 0. And on this, C is going to E with an output of 0. These don't care. So I would like to make it, have a trivial dependency. So I would rather send it to E with an output of 0. And this is going to, well, I want to merge A and D1. Oh, wait. So, okay.
So here we will have a choice again.
Here I'll have a choice, that's right. So here I have a choice. So here I can put, so here I can put D2. I can put D2 0, or as you can see, I have a choice. So there I can put it as D1 also. So as you can see, both of them again give rise to trivial dependencies. All right. So this is, this is how you can split the states. And well, so depending on the choices that you make, you can actually have 4 different transition tables. All right, because you had options at 2 places. So, 2 options at 2 places. So you can have 4 different transition tables. All right, depending on the choice that you make. Okay. So this is how. So this is an important step because, as you can see, if you do state splitting, you are able to, bring it down to 3 states, whereas if you don't resort to state splitting, you're left with 4 states. All right. So I think with this, we can say that we have studied the optimization of incompletely specified sequential machines. So optimization of completely specified sequential machines is much easier. And there, it can be shown that the equivalence partition is unique. In fact, I have equivalence partition is unique. So the argument is given. It's a simple argument. You can go through it yourself. So that means, so long as you get an equivalence partition, it's good enough for a completely specified FSM because it is unique. So the equivalence partition, any equivalence partition that you get, that's it. But over here, as you have seen, it's not unique. The minimal machines are not unique. So you have to be, you have to do it very carefully. And then you might also need state splitting, as you have seen. So that makes the minimization of incompletely specified finite state machines more, um, more interesting exercise. All
Sir,
right. Yes.
sir, can we allow D1 and D2 to be compatible?
Well, D1 and D2 will not be compatible because if you make D1, I mean, you can choose D1 and D2 be compatible, but if they are compatible, then you will find that you can't really go ahead with the minimization because the idea of splitting D into D1 and D2, see, if you could, if D1 and D2, if you could keep them compatible, then you would not need to split D into D1 and D2, right? So because you want to split D into D1 and D2 so that say D1 can merge with A and D2 can merge with C, where A and C are incompatible. So that means you're going to make some choices for D1 and some choices for D2, which will make them incompatible with each other so that they can in turn be compatible with A and C respectively. All right. So yeah, so when you're splitting a state, you don't try to make the two states, two incarnations of the state compatible, because if you could keep them compatible, you would not have to split the state, right? Okay.
So, like, in order to make them compatible to the states for which we split, the split states will obviously be incompatible with themselves, right?
Yeah, that is the idea, because if you could keep, I mean, if you did not have to do that, you would not have to split the state in the first place.
Yes, sir.
All right. Okay, so with this, I think we can close.
No, so CRM one discussion. So next Wednesday we are having a test.
Oh yes, yes.
And that will be an online test.
Yeah, so the exact syllabus will be posted on WBCM, right? So
okay. So so students, you keep an watch on WBCM.
Yeah, because
we'll post it there, and it will be an online test next Wednesday, 2 hours, 8 to 10. Okay.
Yeah.
And CRM, one more request they made is that since many people are traveling, can tomorrow's class be online so that they can attend in online mode? And from next week, it is fully online.
We'll keep it offline. Those who are traveling can, because we are, even when we are doing it offline, the class, we are doing it on Teams. So we'll do it in the class, but they can also it's hybrid mode class. Yeah.
We'll do it in a hybrid mode. And from the next week, we will, except for the exam, we'll have it in offline mode.
Yeah. Okay. Okay. So we can we can just start another topic. And
no, today we don't have time. CRM, you leave it today. Already only 10 minutes left.
No, Pavitra, we got 10 minutes more, so we'll just start and then we'll continue.
Then maybe I'm sharing my screen.
No. I'll start. I'll start another topic. Don't worry. We'll take up your topic a little later. Okay. All right. So let us stop this now. I think I will save this. Keep it. All right.
So CRM, should we discuss a little about the D flip-flop and JK flip-flops?
Yeah, we'll discuss that a little later. I think we'll just, we'll just, Already got it open. Okay. Yeah. So so far we have been. Okay, I think we can close this now. Yeah. So far we have been looking at synchronous FSMs, right? We have been looking at synchronous FSMs. So now let us look at asynchronous FSMs. So first of all, let us just understand how it can how sequential system can work in the asynchronous mode. Let us just understand that much. So here is what we call a flow table, right? This is a flow table. So let us just understand this flow table. So I think just a minute. Yeah, sorry for the interruption. Okay, let us just. Oh, sorry. Okay, so this is that. So now what we are having is, so let us say that, okay, these are your inputs. These are your inputs, right? These are your inputs. All right. Now, let us consider this situation. So here, what it is saying is that when the input is 0, 0, you are in this stable state. Okay, you're in this stable state. So let us call this state 1. Okay. So in this state 1, your stable output is 0. Okay. Your stable output is 0. So for the input 0, 0, your stable output is 0. All right. Now you allow a single input change. This is SIG. Single input change. So only one of your bits can. So only these. So if you call this input states, input. or you can call this, you can call this input states. So your input states can from 0, 0, it can either go to 0, 1 or it can go to 1, 0. All right. So you probably have noticed the Carnot map, like designation of the input states, so that the adjacent ones, the adjacent states are placed adjacent here. So this is so from here, so this is not permitted because you are having multiple input changes. So these are all not permitted. You can have only a single input change. So here what it is saying is that if the input changes, so if it is 0, 0, you stay in state 0, 0, and the stable output is 0. Now, if the input state changes to 0, 1, it makes a transition. So it makes a transition to the state 2. Now here we do not write the output because we allow the output to be undefined for now. I mean, this table does not enforce the output because it is making a change from say 0 to 2, and then for this input 2 is the stable state. Okay, so this is the stable state here. This is the stable state here. All right. So this is what is happening. So from 1, it is making a. Now, if it changes to 1, 0, it makes a transition to 4. Again, here the output maybe something may not be 0. So we leave it. We don't define it here at the moment. And then, as you can see, for the input 1, 0, and 4 is the stable state. So it is stable here for 4, and the output here is 0. Okay, the stable output is 0. Okay, now you can do a similar analysis, or you can check for 2. So in 2, if the input changes back to 0, 0, it makes a transition to 1, and then, well, this is a stable state for 1. All right, and if the input changes from 0, 1 to 1, 1, it makes a transition to 3. Okay, and the stable output of state 3 for the input 1, 1 is 1. All right. Now you can also you can check what's happening for 4. So from 1, 0, if it changes to 1, 1, so it makes a transition to state 5, and then the state 5 is also stable for 1, 1. Okay, with the output of 0, and if from 1, 0, if the input changes to 0, 0, it makes a transition to 1, and state 1 again has a stable output of 0 here. Now, if you look at state 3, from 1, 1, you can either input can change to either 1, 0 or 0, 1. So if it changes to 0, 1, it makes a transition to the state 2, and this state 2 has a stable output of 2 for this input. All right. Similarly, it can make a transition to 1, 0. Can make a transition to 1, 0, and this go to state 4, and state 4 has a stable output of 0 here. So we have also seen the transition for 4. Now let us look at the transition for 5. So state 5, if the input changes from 1 1 to 1 0, it makes a transition to 4. And the stable output there is 4. And if this input changes from 1 1 to 0 1, it makes a transition to state 2, and the stable output is 2. All right. So, you know, you understand that, and as you can see, this now you can, you know, you can treat it much like much like it is it's asynchronous, but we can now proceed with you know, optimizing the state in much the same way as we did for incompletely specified machines. So this is a table, you know, that we can consider. We can consider for optimizing this machine much the same way as we optimized the incompletely specified machine. So I think we'll stop here now, and we'll take it up from here tomorrow. Okay then.
Sir?
Yes.
Sir, I had a doubt, sir.